And that moment, as soon as that person looks at the screen, that great mess of all different superpositions suddenly becomes one with it. Makes no sense to me whatsoever.
Welcome, everybody, to Quantum and the Unknowable Universe. Please give a warm round of applause for your host, Ganesh Taylor.
Thank you. The more quantum theory develops, the sillier it looks, wrote Einstein in a letter in the 1920s. Since then, quantum physics has been verified by experiment and has been central to many of the scientific and technological advances of the last century. But the problem that troubled Einstein remains. Quantum mechanics renders the universe fundamentally unknowable. Heisenberg's uncertainty principle means that science is in principle unable to predict behavior. He concluded, elementary particles are not real. They form a world of potentialities or possibilities, rather than one of things or facts. Should we accept that quantum mechanics has made the universe unknowable? And if so, how should we proceed in the way the world depends on our observations? Is science at play in a world of competing models, none of which can ultimately describe the universe? Or is Einstein's hunch right, and we can uncover a theory that eliminates uncertainty and enables the correct description of the universe independent of any observer? To help us tackle these questions, we're joined today by three fantastic panelists. To my immediate right, Sabine Hossenfelder, is an external member of the Munich Center for Mathematical Philosophy who specializes in the foundations of physics, and she's also one of the world's leading science communicators. On the screen, we're also joined by Slavoj Žižek, who is, of course, one of the most famous philosophers in the world, the author of more than 50 books, including most recently Christian Atheism, How to Be a Real Materialist, and his new collection of essays, Against Progress, will be out in October. To my immediate left, we're joined by Roger Penrose, who is one of the world's leading mathematical physicists, and he won the Nobel Prize in 2020 for his groundbreaking discovery that black hole formation is a robust prediction of the general theory of relativity. So this conversation starts with the following question. Should we accept that quantum mechanics has made the universe unknowable? Sabine, I'd like to ask you to start us, please. 3 minutes on that.
Thank you. Well, my answer to this question is no, we should not accept it. I think there's been far too much acceptance of this quantum weirdness. And I hear this all the time, and I see it in the headlines, popular science headlines. There's something strange, something weird. I see this all the time. And I'm very much with Philip Ball, who wrote a book called Beyond Weird, saying we need to go beyond weird in quantum mechanics. We need to understand it better. But I want to go a step further and say we also need to go beyond words. We need to actually find a mathematical problem, not just saying, well, something is strange and I don't like that kind of thing and I would like this to work a little bit better. But we actually need to figure out exactly what the problem is, because only then can we solve it. And I'm of the opinion that the measurement problem in quantum mechanics is a real mathematical problem that requires a solution, of which there aren't many candidate solutions. Actually, Roger Penrose is one of the few that exists, and I wish there were more. And we should be paying more attention to experimental tests of these ideas.
Fantastic. Slavoj, what do you think? Do you think we should accept that quantum mechanics has made the universe unknowable?
I'm immensely proud to be here, and I look at both of you as authorities. What surprises me is usually we philosophers are the ones who engage in crazy speculations, but from what I read, just take the problem of the so-called of the Big Bang. There are those who claim there is the Big Bang. There are those who claim there was no Big Bang. There are those who claim there are repeated Big Bangs. I cannot judge about it. So my solution to this, a very weird sorry to use this term, one, is no, it doesn't make the universe unknowable, but that's what attracted me from when I was in high school about quantum mechanics. What appears to us as our epistemological limitation, unknowable, we cannot know it, it transposes this openness into reality itself. May I just finish with explaining this with a stupid metaphor that is not precise, but I found it in a book. When you are in a video game, reality is not immersed in a video game. Reality is not fully constituted. You have a tree in the background, but since it's not within the rules of the game that you can approach that tree, of course, the tree is not fully programmed, all the details. And I think that the way I read it, quantum mechanics, the basic insight is that it moves in the same direction. Reality itself is not fully constituted. There are gaps in it. Reality is an unfinished project in itself. So I agree totally. There are many things to discover and so on and so on. But my answer would have been that uncertainty. What is uncertainty is, again, part of reality itself. When we talk about wave functions as potentialities and so on, why shouldn't these potentialities simply exist in the sense of some reality, but not our ordinary notion of reality? I'm much more open here. I think that, for example, when Einstein said, dismissed the quantum effects, the spooky action at a distance, well, maybe this could radically change our notion of space. I think that quantum physics does compel us to rethink the very basic notions of our everyday reality. But again, my idea is this one. Imagine God as a programmer, which is not, I'm an atheist. Isn't it that the lesson of quantum physics is that, in some sense, quantum physicists had, as it were, sorry for the vulgarity, thought God with his pants down, in the sense that God thought humans will never go deeper than atom. We went there and we got a lazy God. So the problem is, without God, can we think, is it possible to think reality as in itself ontologically simply incomplete, not fully structured?
Fascinating. Thank you for that, Slavoj. Roger, what are you thinking about quantum mechanics and it making the universe unknowable? I feel you should have an opinion on this too.
Well, I think there's one thing I agree with the other speakers about, that it's wrong to say it's unknowable.
Fantastic.
That's
Let's move on
that side too. Yes. It doesn't mean that it's deterministic, which is a completely different question. But one problem about quantum mechanics, I think that people think in the following way. They think of quantum mechanics is really about small things like atoms and molecules and things like that. And big things are made out of small things, so therefore the laws apply equally to the big things.
Right.
And this is puzzling because for an atom it could be here and it could be here, or it could be here and here at the same time. And you have to consider quantum mechanics works in that way. There's this thing called the superposition principle, which says if there's one thing can happen and if there's another thing can happen, then you have superpositions where both happen at the same time. Now, I put forward an argument quite a long time ago, actually, several arguments, but only one, which I think I really trust, which asserts that the quantum state, these superpositions like that, will persist only for a certain length of time. And this is to do with trying to bring together the two basic principles of quantum mechanics and general relativity. Quantum mechanics, it's the superposition principle, which I just referred to. General relativity is the principle of equivalence. that really goes back to Galileo. He made a clear comment. I think the one I like the best is talking about fireworks, and the fireworks come out and they make this beautiful spherical pattern. And as this spherical pattern of sparks fall to the ground, it remains a sphere. It doesn't get flattened or stretched or something like that. It's as though the particles don't notice gravity. And this is well known now. You know, astronauts, they can be in a capsule and they look down, there's the Earth. They're not that far up that the Earth effects disappear. No. They effectively disappear because they're falling freely. And the principle of equivalence says that you can locally get rid of gravity by falling freely. And it turns out that these two principles, the principle of equivalence and the principle of superposition, are not quite consistent with each other. So I did a little calculation at one point to show that you can fix this by saying that the superpositions have a lifetime. So the thing can be here and here at the same time, but only for a lifetime, which you can calculate. And if it's for something like that glass, for instance, it would be ridiculously tiny. In fact, the lifetime, I can tell you how you calculate it. You take that glass and you imagine two instances of a glass on top of each other, pull one away from the other, and ask how much energy that would cost you considering only gravity. Sure, nuclear forces, electric forces, that would be huge. But forget all those, it's only the gravitational effect. And the amount of energy that pulls you apart is the critical thing. And it's basically the reciprocal of that energy which gives you the lifetime, in standard quantum mechanical units, which gives you the lifetime of the system. For that glass, it would be an instant. For a flea's eye, people call about that, this thing called the Planck mass, is about the mass of a flea's eye. Even that, if you put that in a superposition, it would be a tiny fraction of a second. It would be 1/30th, or I forget what the number is.
It's okay, you don't have
number
to do
with 30 digits, I think.
You'll be forgiven for not knowing that off the top of your head. Okay. I'm now thinking about flea's eyes, to be honest. Okay, so you don't think so either. The next question we were going to address was, does the world depend on our observations of it?
Oh, I see. No. It's nothing to do with people looking at it.
Okay.
You see, observation is a red herring, in my view. I mean, many people thought, well, maybe the thing which reduces the state. You see, if you just followed, let's say, following the Schrödinger equation, which tells you, if you know what the state is now, quantum state, and that's a well-defined thing, if you know what the state is now, then it tells you what the state is tomorrow, or 10 minutes, or 100 years from now. The trouble is, it doesn't. And it doesn't follow the Schrödinger equation, because at some point, what's called the collapse of the wave function takes place. Now, people tend to think that's ridiculous. I mean, what do they mean by the collapse of the wave function? So they tend to think it's the observer coming along and looking at it. And this is the fault, largely, of the terminology used, that it's sort of an observation.
Right.
And making an observation is supposed to collapse the wave function, because only then does somebody actually see it. But in my view, that's not the right way of looking at it. Somebody seeing it or not is completely irrelevant. It's the fact that a big mass has moved, and then there is a lifetime, which means that this superposition has a well-defined lifetime, and it has nothing to do with anybody looks at it or not.
That's interesting. I mean, I'm no physicist, Sabine, but there's that famous double slit experiment and various other things that show that, you know, if there's an observer, the way a particle behaves is different, right? That's at least how, in principle, we're taught about these things. And Roger's saying he doesn't buy that one bit. He thinks it's sort of intrinsic to the sort of mass of the object being moved. What are your thoughts?
Well, so strictly speaking, I guess I would have to disagree with a Nobel Prize winner, which is always awkward. But so I think that strictly speaking, whenever we observe something, we need to interact with it. So we affect it. There's no way around it. It's just that in many circumstances, it doesn't play any role. Like if I observe a boulder falling down or something, then yes, I have to interact with it because the light scatters off, but the boulder doesn't care. So we often neglect this. Now, when it comes to quantum mechanics, this role of the observer is often conflated with some conscious beings, like someone who actually does the observing. But in the mathematics, that never appears, which I think is what Roger is getting at. So we have something that we call a measurement, and that's just a mathematical process, and it's the collapse of the wave function. It doesn't really make any sense. And I entirely agree that we need to understand this better, and it's probably got nothing to do with the actual act of observation by a human being or even by a robot. It's something intrinsic to the system, could have something to do with gravity, or it could be some entirely new process, like there might be some new phenomenon playing in that needs to be parameterized or what have you. So I think that's probably what's going on. So I think I agree and don't agree at the same time.
Fair enough. Slavoj, perfect timing.
My problem is the same as Sabina, but maybe just in the opposite direction. I agree and agree with the opposite opinion. My problem is this one. I'm speaking as a benevolent philosopher who tries to reach a little bit beyond this endless popular fake introduction. There are what I will use a wrong term, would have called objective theories of collapse. You put them either at the level of time, which can be different for different objects, but simply after a certain amount of time, there is a collapse. There is another theory that I often found, which is that space is the function, that after you get particles which are of a certain greatness, amount, automatically collapse happens. Then, as with observation, collapse and observation, here also I'm just as a benevolent observer confused, because I agree that this is the big problem for quantum physics. But again, we have this, multiverse theory, that there is no collapse, just endless universes. Then I got this from Carlo Rovelli in Helgoland. I think his theory is that whenever even just two tiny particles interact, in some sense, one is already observing the other. And so on. On the other hand, we have, I hope I will pronounce his name correctly, Fagini, for whom, and I'm a materialist, I don't buy this, but it's a crazy theory, for whom the collapse of superpositions means that even the tiniest part has not only some kind of self-awareness, but even free will. That this uncertainty means even in the tiniest particles, there is free will. I don't agree, of course, with this, and I also don't accept the notion of consciousness if for no other reasons than for the reason that in our even conscious experience, but that's another topic, me as somebody versed in psychoanalysis, I think the key decisions that we make are never conscious decisions. A pathetic example that I often use. Think about falling in love. You never fall in love. It's never now I look around, oh, I choose you, I fall in love. All of a sudden, you become aware that you already are in love. A question for Roger. I respect and agree with your big argument that consciousness is not calculable. Your interpretation, reference to Gödel's theorem, and so on and so on. But again, nobody will probably like this solution. But you know what's no science behind it, philosophical intuition, is that, yes, it's non-calculable. But this doesn't necessarily mean that there must be some higher principle, some deeper mind which cannot be calculated. I am more and more convinced that the non-calculability, which involves a certain inconsistency, disparity, and so on, is the thing that maybe gives birth to consciousness. Consciousness is for me always rooted in something that I cannot but call a malfunctioning of a certain apparatus. You know, it's like another of my backstage maybe jokes. I think all new great things emerge from malfunctioning. For example, a French friend of mine gave me the best theory of French cuisine, that they were doing cheese and they were doing it carelessly and the cheese started to smell bad. And then they said, oh my God, why don't we make out of this a more exquisite product and so on, bad smelling French cheese or champagne. Something went wrong with wine, with some fermentation. They said, okay, you see what I mean? When things go wrong, I don't think we need a higher dimension. I believe that the deadlock itself can generate the higher dimension.
Fantastic. Well, I think I've just realized I've fallen in love. But also, on a serious note, okay, so we're talking about whether or not there's a function for a conscious observer or not in our understanding of the world, right? What is the relative importance of interaction in this sort of understanding of the world? And the sort of next thing that we wanted to talk about actually was whether or not Einstein was right that God does not play dice with the universe. And Roger, you've sort of touched upon this already about this question of determinism, essentially. And I think that ties in with what Slavoj has just been telling us about as well, this idea of consciousness and randomness. And, you know, do you think Einstein was right about that? That God, if there is a God, does not play dice with the universe?
That's a different question. You see, I'm trying to say that the collapse of the wave function, which is normally considered a random process, you just get a probability for it to doing, the particle is in a superposition of being here and here, and then it collapses to being either here or here, but with a certain probability. And then it might do this or it might do that, and that's all you can say. Right. Now, I'm less happy with that. I'm not saying that it's not random. I don't mind if it is random. I don't think it is exactly the answer that it's random. I think there's something much more subtle. And then you bring it in this issue of a conscious observer, which at this stage of the argument is a red herring. It's also a red herring which I like to play with, because I do consider this as an important question, but it's not a question which comes in at the level of whether the collapse takes place, when it takes place. I regard that as an objective process which has nothing to do with whether anybody looks at it. I like to consider a following, if I can tell a little story. I imagine there is a planet out there somewhere a long way off, which is very much like the Earth, just like the Earth, except for some reason life never got started. Now, consider the weather. The weather is supposed to be what's called a chaotic process, that it depends on little tiny effects. People often talk about a butterfly. Its wings flap this way rather than that way, and it makes, eventually the other does that rather than this. Now, on this planet, there aren't any butterflies. There's certainly no human beings, no nothing like that. So that on this planet, according to that point of view, the weather would be a superposition of all possible weathers, a great mess. Now, the space probe goes up, it's aimed at trying to take a photograph of this mess and propagate it back to Earth. Several light years away, it takes a long time to get there, and then it takes a photograph of the planet with this mess of superpositions of all possible weathers. It comes back, and as it gets to the place where it's within communication distance from the Earth, it sends a signal to the people on the Earth, and somebody's looking at the computer screen, and that moment, as soon as that person looks at the screen, that great mess of all different superpositions suddenly becomes one weather. Makes no sense to me whatsoever.
Right.
It's already decided to be one weather or another way before that happened. It's nothing to do with the conscious observer sitting in and looking at the television screen to decide which way it's gone. Now, when I say it's nothing to do with it, that's not quite what I mean when we look at it the other way around. What is consciousness? But that's another discussion altogether. We're not talking about that here, I think. At least I don't know if we are.
We can diverge.
You see, I do take the view that the other way around is important too. That is to say, whatever the deep laws of physics are, they are, as they currently exist, computable. And I had an argument, I still think I believe it, a long time ago, which was when I went to a course, nothing to do with what I was actually doing on mathematical logic, and I learned about Gödel's theorem. And I was extraordinarily impressed by it, because what it said was, if you have a device which acts according to computable laws, then you have a statement which you may construct out of how the machine is made. And that statement, it's asserting its own falsity, basically like that. And the thing is that just setting that on the basis of these computable laws, and you can see that what it's doing, it can't be a computable decision. That's the idea. So I formed the view that conscious understanding, which is what enables you to understand why the Gödel's theorem is true, if you like, it depends on knowing not the rules which the system is based on, but knowing why they worked, which means understanding why they only give you truths. Why do these rules, which gave you truths from a previous truths and going to give you form, and that process, which is a completely computational process, how do you know that the answer is true? And the Gödel statement tells you why it's true. And it's true not because it follows the rules, but because you know that the rules only give you truths. And that's a subtle difference. You know that following the rules only gives you a truth. And that tells you that the statement is truth by virtue of your knowing that the rules only give you truths. It's an amazing thing. You really have to see it to see why this works. But it tells you that your understanding transcends the following of the rules. So the question, what is understanding? Well, it's something that seems to involve consciousness. Because you can say, well, if an object understands something, it must at least be aware of it. It doesn't make any sense to say it understands it without being aware of it. That's just normal language. So I would say that normal language is probing something really important. It's got to be conscious to understand something. So I'm trying to say that the quality of understanding is not computable, and therefore is something beyond what we understand in current physics. And the claim I'm making that it's what really goes on in the collapse of the wave function. But it's a completely different story, and I shouldn't really have gone into it here.
Slavoj, yes, please.
I want to manipulate in a very nasty way and get Sabine on my side against Einstein, mainly. Sabine, I enjoyed one of your last books where you explode against aestheticization of physical science. It must be a beautiful, simple formula and so on, and you brutally oppose it. I deeply agree with you because I think that although Einstein didn't believe in a personal God, when he says God does not play dice, what he meant, there are many quotes, is precisely, for example, God who reveals himself in the harmony of all that exists, the universe is marvelously arranged, and so on and so on. So if you say God doesn't play dice, my answer, without involving God, is we all know, I hope, what Niels Bohr's answer to this was. Don't tell God what to do or what not to do, to play. I think that Einstein was here very clear, precisely along the lines outlined now by Roger. He said, and I don't agree with him here, that there is no science without religion. Religion in the sense of trust in some higher natural order that waits there to be discovered, and so on and so on. No, my idea is precisely that universe is such a mess that I wouldn't even use the term universe, because it brings out, at least for me, all those old mythological thinking which survives in, universe as the big unity, and then what is the basic unit? Is it fire, water, and so on? No, universe is an irreducible mass there are local necessities which emerge, but always in a contingent way. So paradoxically, I think that although Einstein denies a personal God, he is, for me, still, and he said this, basically a religious guy, because he believes in this higher harmony of the universe. And I think that if there is a lesson of quantum mechanics in all its versions, is that no, we have to drop this. In this sense, although quantum mechanics, and I hate those guys who do this, is often given some kind of a fake spiritual twist, like, you know, all this instant communication between two particles prove that there is a higher spiritual connection outside time, space, and so on. I claim that no, quantum mechanics is the only radical materialist theory. As you already said, all of you, observation does not mean there is reality, we are somewhere out. The paradox of observation advocated by quantum mechanics is that precisely we are in reality. We are a part of reality. We are not outside, which is why I will name now somebody whom I respect politically but not philosophically. For me, the worst idealist is Lenin in his materialism and hero criticism, where he talks about objective laws, all preemptive. Yes, but where does he stand? From what position does he do this? I think quantum mechanics is deeply materialist because it includes us into reality. Sorry if I was too long.
Oh, I wasn't expecting to hear about Lenin in this debate, but I'm glad he's joined the chat.
Maybe I could say something for the sake of context, because we've been talking about Einstein's quote that God doesn't play dice. I think it's good to remember what he was actually referring to, because I agree with Roger that it's kind of the wrong question to ask, but he had a reason to ask this question. And Einstein was thinking of a very simple experiment, though he was considering it as a thought experiment, where you have a quantum particle which you send through a very small slit, so you know where it is, basically, and it goes through, and the wave function of the particle spreads out into all directions. But when you observe the particle, it's only in one place, so that wave function suddenly has to focus. And so the moment that you measure the particle, say on the right side, the wave function on the other side has to know to disappear. And it has to know that instantaneously, faster than the speed of light. So this is what Einstein called spooky action at a distance. And clearly he didn't like it because it was violating his theory of special relativity, according to which nothing can go faster than the speed of light. And so he said, actually, the particle needs to know where it's going already by the time it started traveling. And it's determined by some kind of hidden variable. That's what they were called. And that reintroduces determinism. And this is why he was talking about, the question, does God play dice? Is the universe actually non-deterministic? It was because he wanted to reinstate a locality to make the theory compatible with relativity. And so I think that this question of determinism is kind of misleading, because what he was trying to get at is really locality.
That was very helpful, Sabine.
Just a stop question to Sabine, because this interests me immensely. You used words which to me appear, sorry for this expression that you hate, weird, but weird in the most provocative sense. You say particle must know. Particle knows from the beginning. Why don't you simply say it's in the nature, in the objective structure of a particle to follow this path? Why did you use the term knowledge?
Well, that's just a word. As I said in the beginning, we need to go beyond words. So what I'm trying to do is I'm trying to I'm trying to use English to explain equations that I have in mind. And I agree with you that maybe saying it knows is not a good way to say it. I'm not trying to say that the particle has some kind of brain and it decides where to go. It's just some variable you can use to calculate what's going on.
Does that relate to what you were saying, Roger, about having a sort of sense that the sort of collapse of the wave function could be random, but maybe is a little bit not random?
I don't know whether I should go into this, but you see quite a subtle issue, particularly the thing about, if it collapses, how does the part of the wave function over there know to collapse, et cetera, et cetera. Now, the thing is, I probably shouldn't go into this, but let me do it anyway.
All right. Yeah.
I had a long time thinking about this, really, before I thought about it, that in order to understand the timing of collapse of the wave function and that sort of thing, it's a really subtle issue, and one can really only understand it in the sense that you have to have what I call two kinds of reality. There's what I call quantum reality and classical reality. In classical reality, you can ascertain. I can say, hello, glass, what's your shape? And it says I've got a circle at the top and I'm pretty well parallel all down there, et cetera, et cetera. So classical reality, you can ask a question about it and it can answer very directly. Quantum reality, you can only confirm. So it's a distinction. And it was a thing due to Einstein, actually, when we're talking about Einstein here, is questions how real is the wave function? And you can think about the simplest quantum system, really, is the spin of a spin-half particle. And it can spin right-handed about the up direction or right-handed about the down direction, and you usually talk about the direction in which it's spinning. It really means right-handed about that direction. And the different directions, there are really two states, up and down, and then all the others are superpositions of those two. Now, can you ascertain, I've got a free electron here, which is just on its own here. Can you ascertain what its spin is, where its spin is pointing? No, you can't. But if you had somehow, in the way that was produced, some machinery and all that stuff, by now you say that the electron would be spinning about that axis. And you can confirm that. You can do an experiment which says, hello electron, is your spin about that axis? And you 100% certainty, that's to say, you can repeat the experiment many, many times, 100% certainty you get it right. So you can confirm it. If you didn't have it right, it would say yes sometimes, no other times. So this quantum state, that can be confirmed, but it cannot be ascertained. And this is how you get around the various paradoxes that are involved in special relativity. Then you send signals into the past and all that kind of stuff. It sounds pretty crazy when you look at it, but it doesn't lead to a contradiction because it's quantum reality. And quantum reality you cannot ascertain. You can only confirm. And so that's the way you get round of the problems. I can say, what is real about the universe? We have to be careful. You mean quantum real or classical real? And it's not quite the same question. And most things we talk about are pretty big, and so we're talking about classical reality all the time. And so that's a reasonable kind of thing to talk about. But when you're talking about quantum experiments and quantum systems, you've got to worry about it, especially when they're what's called entangled. You have two particles which doesn't individually have a state, but it's only related to another one.
I mean, you'll forgive me, I'm not a physicist, but aren't those two things related to each other? Isn't that where the problem comes in? I mean, of course, the glass is a classical reality, but if quantum mechanics is real, then it is also within...
But it's so big, you see, that the collapse is settled its state. It's so pretty, I think the quantum reality and classical reality are pretty well the same.
So is it a matter of levels? Effectively, you're saying that the quantum reality only exists in sort of one level, and it's not one that we really have much access to because all the things that we interact with are at a level that mean that the quantum rules no longer apply.
I think that's roughly true, yes. Only if you're doing a quantum experiment, you see, deliberately something quantum, and you're trying to ask it a quantum question.
Only then the rules.
Then you have to worry about the quantum reality.
Would you agree with that, Sabine?
Yeah, roughly, yeah.
Good job. Okay, fantastic, everybody.
A brief question to both.
Yeah, please, Slavoj, please.
I read correct me if I'm wrong and it was bullshit what I read. But in one of the, I admit it, popular introduction to quantum mechanics, I read of this, what they call borrowing from the future. If a particle can do something as if borrowing the energy to do it from the future, and then when the moment of reckoning comes, it already self-annihilates itself. It is as if we have an objective social order, and you can move in a shady domain before what in my psychoanalytic jargon I would have called the big other, the order of our ordinary reality, notices it. It's as in, sorry for again a popular metaphor, you know, my favorite thing in all those cartoons, Tom and Jerry, was that, you remember, I always use a cat gets close to the precipice, then it goes on walking, and nothing happens. Only when the cat looks down, oh my God, but there is nothing down, it falls down. According to some readings, doesn't something similar happen in that shady quantum domain before this quantum domain has its effects, but at another level? I deeply agree with this notion of quantum reality as different from ordinary reality, and I agree with, if I got it correctly, and brutally correct me if I'm wrong, that the key problem for me is the following one. There are some physicists, and even some, this may surprise you, pseudo-Marxist leftists who transposed onto this duality, quantum reality, ordinary reality, this boring Marxist topic of life process, creative life process, and then its reification. And they claim as if quantum waves are the domain of physical freedom, everything is open, and then you have alienation, reification, and so on. No, the big problem for me, I don't have an answer, but for this, to get an answer from any of you, I am, sorry for my vulgar metaphor, ready to sell my mother into slavery. It is. What must go on already in quantum reality that pushes it towards collapse? There must be already there. Quantum reality is for me not some happy domain, everything is possible and so on. No, it must have a certain impossibility, tension, and so on. I'm speaking very naive terms, and with all respect, I am now turning to you.
Yes. Slavoj, I think Sabine can answer your questions.
Well, I'm not entirely sure I understood the question, but I can say something about this problem of borrowing energy from the future and stuff like this, because I was recently thinking about this, and I think this will make a nice closure, which is why I've come to agree with Penrose that the collapse of the wave functions got to have something to do with gravity. So forget everything about complicated quantum experiments. Just imagine you send a single photon through a beam splitter. So beam splitter does what the word says. It splits a beam. So the wave function of the photon has a 50% chance of just going through and 50% chance of being reflected. And strictly speaking, this creates an entangled state with the beam splitter. So you have a 50% chance that the momentum is actually redirected and the recoil is picked up by the beam splitter. And in the other event, nothing happens to the momentum. Now, the issue is the following. So you have some momentum going to the left and some momentum going to the right. And momentum is a physical thing, like you can measure it. It's definitely there. It's so small for a single photon that we can't in practice measure it, but it's something. And so the moment the wave function collapses, this energy and momentum that went to the one side in your mathematics needs to go to the other side. How did this happen? It's not compatible with Einstein's theory of general relativity. That's just mathematically not possible. And so if you try to make this work within quantum mechanics, you need to do some weird thing where, you know, the energy from this particle actually went back into the past and then forward to the other side. And I think this is where these stories come from about retrocausality and mixed up causality and whatnot. But what I learned from this is that we need to think about how to quantify this energy so that it's compatible with general relativity, because this is where the energy momentum conservation really comes from, which means it's got to have something to do with gravity.
On that note, please can we thank all of our wonderful speakers for joining us today. Thank you to the audience. Enjoy the rest of your festival.